right there. Here are a few example problems that I'd like to discuss on how we can find the probability of a given event, given information about the union and or the intersection. And this, I'm only going to do 3 examples on this, but I'm going to kind of structure the 3 examples as if these are typical types of problems that you're going to see. The first one being 2 dependent events. We're going to talk about another example if you know that the events are mutually exclusive, or what we call disjoint. And then the last example is going to deal with if the 2 events happen to be independent. And in each one of these problems, what I'm trying to find is I'm trying to find the probability of one of the events happening, but it's going to give me a bunch of information about multiple events and things of that nature. So let's take a look at this first example. This first example says a recent survey was conducted in a small town in Ohio. The following data was found. 42% of households own a dog. So I'm going to call that event D as owning a dog. So the probability of owning a dog is 0.42. The second part says 86% of households own a cat or a dog. So the probability, and for cat I'll use C, of cat or dog is 0.86. So 86% own a cat or a dog. And then the last one says 7% of households own a cat and a dog. So that would be the probability of cat and dog equals 7%, so 0.07. Okay, so what does the problem ask for? Well, the problem asks us to find the probability that a randomly selected household owns a cat. So this is just wanting us to find what is the probability of a cat, probability of C. So in order to do this, you need to know, you have to have a real good grasp of what the formula for the union looks like. So in this example, and I'll use the C's and D's for cats and dogs, we need to know that the probability of the union, so cat or dog, is equal to the probability of each one of them by themselves. So cat plus dog individually minus the intersection. So the probability of cat and dog. This is a formula or a setup that you want to make sure that you have memorized going in, especially for the OST, but going into a study of probability. And those letters could change. I could do A or B is the probability of A plus the probability of B minus the intersection. But the union of 2 dependent events is always set up as the probability of one event or the other event is equal to the probability of the 2 events individually minus their intersection. This is a universal truth in probability. So now it's a matter of just plugging in information that I know. So this is 0.86 equals the probability of cat. That's what I'm trying to find. So I'm just going to leave that one alone. Plus the probability of dog is 0.42 minus cat and dog is 0.07. So I can clean this up just a little bit. I have 0.86 is equal to the probability of cat plus 42% minus 7% is 35%. Just combining those like terms over there on the right, 0.42 minus 0.07. And now to solve for the probability of cat, I have to subtract 0.35 on both sides. And let me grab my calculator here. And 0.86 minus 0.35, some of you probably already did this in your head, 0.51. So that means what percentage, or what is the probability that a household owns a cat? Is 51%. There's a whole lot of cat lovers out there, I guess. I am not one of those people. I don't think my dog would appreciate me bringing a cat home. So that's how we do a problem where we have to find one of them if the two events are dependent on one another. All right, so here's another example, and this one's a little different. This one is going to talk about mutually exclusive, or what we sometimes call disjoint. It means the exact same thing. So if I have mutually exclusive events or disjoint events. So let me actually back up a slide. When I have dependent events, my Venn diagram looks like this. And my two circles will overlap one another. And not everyone in the population has to be in one of the two circles. Some of them might be in both circles, some will be in just one, some will be in just the other, and some will be in none. That's dependent events. Right? When I look at mutually exclusive events, mutually exclusive events means that the two events do not touch at all. The intersection is 0. So there's no way to do both of them at the same time. And some events that you might have might be you cannot take your math test and get an A and a D on it at the same time. They're mutually exclusive. If you get an A, then you can't get a D. Those kind of things are what we talk about when we talk about mutually exclusive. So here's a problem where it says Joey plays baseball for his high school baseball team. The team manager determines that the probability that Joey gets a hit is 40%. So the probability, I'll call it H for a hit. Probability of a hit is 40%, or 0.4. For those of you that know a little bit about baseball or softball, this is what we call your batting average. So your batting average is 0.400. That would be 40%. It says the probability that Joey gets a hit or a base on balls, which is called a walk. So the probability that he gets a hit or a walk. So this is what they call on-base percentage. Is 0.56, 56% of the time. So since Joey cannot get both a hit and a walk in the same plate appearance, these two events are going to be mutually exclusive. So it would look like this. This could be the probability of getting a hit, and these could be all of my walks. The only difference, I am going to do this exactly like I did the last problem. So the probability of hit or walk is equal to individual ones. Probability of hit plus probability of walk minus the intersection. So probability of hit and walk. The only difference is when I know that they are disjoint, then this piece on the right side is a 0. That piece on the right side is a 0 because it is impossible to have a plate appearance where you get a hit and a walk at the same time. You're only going to have either a hit or a walk or an out. So I'm plugging everything else in. The probability of hit or walk, we said, was 0.56. We said the probability of hit was 0.4. Plus the probability of walk. That's what the problem asks me to find. It says find the probability that Joey will walk. So I can combine like terms on the right, just like I did before. This one's even easier because 0.4 minus 0 is still 0.4 plus the probability of a walk. And then I'll subtract 0.4 on both sides. So the probability of walk. 0.56 minus 0.4 is 0.16. So what is the probability that Joey gets a walk? He will walk 16% of the time. So we use the exact same setup as we did before. The difference is knowing that we have mutually exclusive events means that my intersection is going to be a 0. Right? Those two, I think, are the easier of the two. This last one is the one that sometimes gets a little tricky. And this is independent events. Now, just so you know, independent events cannot be mutually exclusive. So they do have to be, they have to cross over kind of like dependent events do. All right. But one of the things you need to know about independent events, and probably the most important, and this is what separates them from dependent, is that the probability of A and B happening is equal to the probability of A happening times the probability of B happening. This is called the multiplication rule, and this is one of the rules that we'll use to test and determine whether two events are indeed independent of one another. So if this statement is true, this is one of three ways to prove independence, and I believe in our module it is the third way that we prove independence. So let's take a look at a problem. We're going to set it up the same way, but we're going to use this new information that we have. So it says the probability that it's raining outside is 30.3 or 30%. So I'm going to call that R for raining. Probability that it's raining is 0.30. The probability that you earn an A on your test or it is raining outside is 0.62. So the probability of earning an A or it's raining is 0.62. The next sentence says, we know that the weather outside does not affect your chances to get an A on your test, so the two events are independent. So what is the probability that I get an A on my test? What is the probability of getting an A? That's what I'm after. So just like the first two problems, I will say the probability of getting an A or it's raining is equal to the probability of getting an A plus the probability that it's raining minus the probability that you get an A and it's raining. Now, because you know these are independent, this piece right here, I'm actually going to rewrite as I did up here at the top. And the only reason I get to do this next step is because I know that my two events are independent. So the probability of A or R is equal to the probability of A plus the probability of R minus the probability of A times the probability of R. Alright, so now I can start subbing some stuff in. Probability of A or R, I know this is 0.62. This is equal to the probability of A, I don't know it. Plus the probability of R is 0.3 minus probability of A times the probability of R is going to be the probability of A times 0.3, so this is going to be 0.3 probability of A. Alright, now for the algebra, and this is where it gets a little bit tricky. First thing I'm going to do is I'm going to combine like terms. However, you need to see where the like terms are. Those are my two like terms. I have one probability of A on the left, and I have -3 probabilities of A on the right. So when I combine these like terms, 1 probability of A minus 0.3 probabilities of A will leave me 0.7 probability of A plus 0.3. So I'm just combining like terms. That's actually a 1 right there. 1 minus 0.3 is 0.7. So I'm going to subtract 0.3 on both sides now. So that's going to give me 0.32 is equal to 0.7 probability of A. And since that is 0.7 times the probability of A, I'm going to have to divide both sides by 0.7. And the probability of A is going to equal 0.32 divided by 0.7. And according to my trusty calculator, that probability is about 0.4571. It's actually a much longer decimal than that, but I rounded it to 4 decimal points. So 0.4571. 0.4571. So that means that this student has a 45.7% chance to get an A on any given test. And for some people, I guess that would be good. I would like to see that like 0.98. That would really make you feel good if you were going into a test knowing that 98% of the time you would earn an A. So this one, the toughest, by far the toughest one, are the independent events. And the reason being is I have to take that last term and I have to kind of switch it based on the rule of independence. Then I'm always going to have a problem of 1 minus some percentage, and it's always going to kind of be set up the same way. So I hope that helps when finding the probability of an event given information about the union and intersection. Odds are any problem you see is going to fall under one of those 3 categories. I hope you found the video useful, and thanks for watching.